Okay. Hi, Erickson. Thanks for making the next tutorial. Let's start now.
Okay. Good morning, good afternoon, good evening, everyone. So today I'm going to continue the introduction to algebraic stuff part 2. As you can see, I keep the title as algebraic stuff because, well, I'm keeping it as vague as possible to save myself. But anyway, today I hope it's going to be a little bit more interesting, but also more technical. And I'm going to present it based on some readings that I did, more like from the direction of high energy physicists rather than the quantum information theories. But I think this is much more instructive than the historical way of how these things was introduced. And as a usual disclaimer, I'm not going to claim that I know a lot of these things in great details, and the reason is actually very simple. The reason is because a lot of results in von Neumann algebras is actually very algebraic in nature, but the proofs and technical details are actually functional analytic in nature, which means that you can actually understand the theorems without really the statement of the theorems if you never took functional analysis, but you absolutely cannot prove anything if you don't have analysis in background. Okay. And again, I will introduce mostly the algebraic ideas, and hopefully it conveys some of the most important properties, and then it keeps you interested to pursue in further directions. So this is roughly what I'm going to go through. I will introduce very briefly the ideas behind von Neumann algebras, the very famous but technical notion of types of von Neumann factors, really. And then I will introduce a little bit of how do people use this in quantum information, like a very small corner of it. Okay, so I'm 5 minutes into 10 o'clock. So let me first show you a few recap that is hopefully very useful. Okay, we've already covered last week why we want to think about operator algebras. It is because one thing is that it gave you a notion of Heisenberg picture, which most of us are familiar with, but more importantly, the GNS reconstruction theorem actually lets you recover the Hilbert space construction that we are familiar with, and in particular, the Heisenberg picture way of doing things is actually much more useful when you are trying to deal with infinite systems, thermodynamic limits, or even the notion of superselection sectors. So the superselection sectors, I'm not going to talk about this in my presentations, but I hope you keep this in mind that in finite dimensions, really Heisenberg and Schrodinger picture were basically the same thing. But in infinite dimensional systems, Heisenberg system often gives you much more clarity than you might think it could. Okay, let me recap the statement of the GNS representation theorem. The statement looks technical, but it really says that, if I give you an algebra and also a state, you can always reconstruct a Hilbert space representation where the state is represented as a cyclic vector. Expectation values look like expectation value, and this representation is unique up to unitary equivalence. And the purity of the state is really connected to the notion of reducibility of the representation. Now, in the language of quantum information theorists, basically Jonas' theorem only says that every system admits a purification. And in finite dimensions, this purification is basically the one you get from vectorization. So if you do the vectorization map where you convert a cat multiplied with a bra to a double cat, which is the purified space, then basically this is up to unitary equivalence, the same thing as the GNS representation theorem. So this is what we talked about last week, and I hope a version of this has been familiar to you, although you never call it the GNS theorem. And I will just give one example to drive this point. So last week I gave the example of a qubit with a maximally mixed state, but now I'm gonna take a qubit whose algebra is a d-dimensional complex matrices, and now I'm gonna take a thermal state, which is represented as a Gibbs state with a density operator associated to some Hamiltonian. Now, in the operator algebraic framework, the Hamiltonian of a qubit is a self-adjoint operator with real spectrum, which means that it is actually an element of the algebra. So the nice thing of the algebraic framework is that even dynamical objects like the Hamiltonian is actually part of the algebra of observables. Okay, and with this example, we can do exactly the same computations as what we did 2 weeks ago. You vectorize the thermal state to get the cyclic vector, and you will get what we call the thermophile double state in high energy physics, or in the quantum optical language, is called the two-mode squeeze state. And then the GNS theorem in this case says that the GNS Hilbert space is actually isomorphic to the algebra of observables, because the thermal state has max rank. And by the notion of vectorization, this is isomorphic to 2 copies of the original qubit Hilbert space. So this really gives you a canonical purification that doubles the Hilbert space. And in fact, this is always true whenever the vectorization has maximum Smith rank, or the density matrix has maximum rank itself. Okay, and you can see that the GNS representation is reducible simply because the GNS representation naturally gives you what we call the left multiplication. So if you think of A as A tensor identity on the second copy, then just by direct computation, you can do it by hand or mathematically, you realize that you can actually write this as just a direct sum of D copies of the same operator. Okay, and that's the end of the example. If there is any question, please let me know, but this is basically just redoing exactly what we did last week. Okay, and as an exercise, I would like to convince you that this is a very worthy thing to try. So if you take a qubit, but now you don't take a density matrix that's max rank. So for example, like the cat0, okay? If you run through the GNS representation, you can show that this state is actually a pure state because it is associated to irreducible GNS representation, and convince yourself that because it is not max rank, your Hilbert space will not actually be a double copy. It's actually a single copy, and that's because you have to quotient the zero norm states of in the GNS representation. Okay, so please try this by hand. It's actually instructive. Okay, and with the examples out of the way, I hope we now can experience a little bit of von Neumann algebras. I must mention again that this is really a big subject that you can make a career out of it, and I'm trying to not do it justice by pretending I know it. Okay, so first, if you look at what we did earlier, right? We can think of a separate problem. So suppose you have a bipartite system in finite dimensions. So you have a Hilbert space A tensor Hilbert space B, and you really want to call them a bipartite system that is independent of each other if you can actually do 2 things. One, you can act only on the subsystem, right? So if you have a bipartite system, you should be able to just do operations only on Hilbert space A, or operations only on Hilbert space B, and they should commute. Okay, and also equally importantly, in principle, you should also be able to prepare states independently. This is what we call the statistical independence. That means you should be able to prepare a global state on the joint system and also a state on the subalgebras in such a way that the expectation values factorize. Okay, in other words, you should be able to prepare what we call a product state on the joint system. If you want to, of course, you can also prepare like a classically correlated state, in which case you just generalize equation 10 to a summation over like mixtures of probabilities, and this can be done. But the crucial thing is that you must be able to do this if you want to make a notion that you have a bipartite system that is completely independent. Now, what is important is that this statement could still be made even if you don't have the Hilbert space factorization. So if you look at just the previous slide, right? I make the assumption that you can factorize the Hilbert space, and then the local algebras script A and script B can be written as a tensor product of identity times bounded operators on the other Hilbert space. But really, you don't have to do this, right? If you have a big Hilbert space, if you take a von Neumann, a subalgebra that is a subalgebra, two subalgebras that commute with each other, that already defines a local subsystems. And if you can satisfy 8 and 10 in principle without knowing that there is a Hilbert space factorization. And indeed, this is actually what we need for people who works in quantum field theory. And this is also one way to motivate the notion of von Neumann algebras. And let's define it more precisely. So the definition is, if I have a Hilbert space, and I take a subalgebras of bounded operators acting on some Hilbert space, really it should be a C-star subalgebra of the bounded operators, then you can define the commutant of this algebra to be anything that commutes with this algebra. And this is a von Neumann algebra if it is its own bicommutant. So this is, or the double commutant. So this is the famous result by von Neumann, which is that if you take a C-star subalgebra of bounded operators, you find all the things that commute with it, and then you find it again, everything that commutes with its commutant, then that's a von Neumann, that would be a von Neumann algebra. Okay, and let's go through this a little bit more. So remember, in the GNS language, you can represent an algebra of observables by the left representation. Remember, there is this left multiplication in the proof of the GNS theorem, and you think of an element of the algebra as basically something like multiplication on the left, which morally speaking is a tensor identity on the purified Hilbert space, right? And the commutant is basically going to look like everything that is identity tensor on the right-hand side with a transpose, if you take the same element, okay? And there are many ways to see this, but you can see that if 11 and 12 were correct, they commute by construction. But if you are more familiar, for example, with the tensor network language, right, this is nothing but transpose trick, right? If I take say a cyclic vector and I have a tensor identity, I can actually do a transpose trick to the other side, and I'll get something like the transpose. And this is actually one way to represent elements of the algebra and its commutant. When I say cyclic vector, this is actually, remember the notion of cyclic vector is something that the action of the algebra gives you the whole Hilbert space. So traditionally in quantum information, the Bell state is the typical example. And of course, the Bell state, we have already seen that it is a natural cyclic vector in the double Hilbert space. Okay. And in the footnote, I make a small comment that is really important. So you realize that the definition of von Neumann algebras require that I take is bicommutant, right? The reason is because usually a C-star subalgebra of bounded operators is actually not necessarily a von Neumann algebras. And if you take the commutant, it is actually a von Neumann algebra. And if you take a double commutant, this is strictly speaking going to be bigger than the original algebra. That's why if you want to make a von Neumann algebra out of subalgebras of bounded operators, you usually take the bicommutant. You just take the prime twice. And that's a very simple construction. So I'm going to give you one example that maybe will escape your mind in this session, but when you look at it on your own, you might try it. So for example, I have 2 copies of qubits, and let my joint algebra to be 4x4 matrices now. Of course, this is going to include non-local operations on both qubits. Now, let me take a subalgebra, C-star subalgebra of just the projection on the top left diagonal. Okay? Now, this is not von Neumann algebra for a very simple reason, because if you take the bicommutant, it commutes with everything that has the B in it in the second diagonal. And therefore, if you put an identity on top, if you do a tensor identity, it is not going to be equal to its bicommutant, because this matrix is strictly small. The set of matrices with rank 1 projectors is strictly smaller than the diagonals. And in fact, if you just study carefully this example, there is actually a subalgebra M3, which is like a 3-dimensional matrices acting on 3-dimensional Hilbert space HAB that commutes with DA, which means this is not a good notion of a subsystem, because that means your B is 3-dimensional, which means your A is 1-dimensional, but 1-dimensional quantum system basically means nothing, right? So in other words, you are not actually partitioning the Hilbert space properly. In fact, you have failed to divide the system into 2 qubits. So that means the dA cannot be the local algebra associated to 1 qubit. So this is more like I guess, is not really an example, but more like a counterexample of how not to think of local algebras. But this is also, sorry, any question?
Yeah, could you explain this double prime? So D prime.
So remember,
yeah,
a von Neumann algebra must be equal to its own double commutant.
Okay.
But dA commutes with everything that is diagonal.
Yeah.
But a diagonal matrix also commutes with itself. So the bicommutant contains all the diagonals, which is bigger than the projection only on the top part. So in this case, the dA is strictly smaller than the double prime. And this goes through even if you took a tensor identity.
So dA prime prime in this case is A sub A.
Let's see. No, it's not quite. Remember that in the purified Hilbert space, you really have to take the algebra should be in the joint algebra, right? A sub A is really more like a one tensor copy. So this is, the way I put the notation is not really very good, but the important point here is that the moment you take double commutant and it in general is going to be bigger than the original algebra you start with, and only when they are equal it is von Neumann algebras.
Okay. And does but we have a finite dimensional case, so we have a von Neumann algebra, yes?
No.
Okay.
So dA is a C-star subalgebra of A.
Yeah.
But it is not a von Neumann algebra. That's why if you want to make it into a von Neumann algebra, you need to take a bicommutant. You need to do a double prime on dA, and that gives you a von Neumann algebra.
So D double prime will be a von Neumann algebra, yes?
Yeah, or in this case, strictly speaking, is dA tensor identity, then you take the double commutant.
Yeah, and that becomes like this extension of dA, and the C-star algebra becomes von Neumann algebra.
Yes, it is actually a very interesting result that if you take a C-star subalgebra of bounded operators, the commutant is always a von Neumann algebra, even though the algebra itself is not. And then the commutant of a commutant is a von Neumann algebra because the commutant is already a von Neumann algebra.
So Erickson?
Yep.
Mayor? So in fact, if you take any subset of a Hilbert space of the bounded operators, you can go from that to construct a von Neumann algebra just by taking the generated set from that set U. So you can exponentiate everything and produce for yourself a subalgebra generated by that subset. And then you can take double prime. So you don't need a C-star algebra to begin with. You just need a set.
Yeah, but I guess the set also you have to be careful, right? You need to include identity, otherwise the exponentiation is not close to the. Oh no, wait, you are right actually. Actually, now I think about it, yes, you don't actually need it to be a C-star subalgebra, but I'm just taking the simplest example where you start with a C-star subalgebra and then you just take a bicommutant. You are right. In principle, you might even be able, I think in the Wikipedia, for example, right, you can actually take some a subset of something.
Right.
Yep.
Right. Okay.
That's right.
Thank you.
Yeah. Very good. Thanks, Peter. So you should also keep in mind that a lot of things that I say here are probably not the most general thing that I could say. But oftentimes it's more than enough to illustrate the point. Okay, so this example is more like a counterexample. So convince yourself that running through this kind of example will allow you to think about how to do bipartitions. But more importantly, to understand von Neumann algebra, we really need to consider like a building blocks of von Neumann algebra, which is called a factor. And the way to think about it is the following. So if you have a von Neumann algebra, then first of all, recall that the commutant itself is already a von Neumann algebra. And then you can ask how much they intersect. So do they share a common element, right? And a factor, a von Neumann factor, is exactly when they share nothing except operators proportional to the identity. And in fact, one can a famous theorem, a well-known theorem in the theory of von Neumann algebras is that U is a factor if and only if together with its commutant, it generates the entire bounded operators on the Hilbert space. So if you take, so the A cup U, the A union, okay, this is actually a math frac A. So the algebra union is commutant means you take all the combinations of the products of these two elements, and then you take the bicommutant. If you get the whole thing, you get a factor. Now, but I think that's probably easier to see through an example. So if I give you a two-dimensional Hilbert space, there is a tensor product of HA times HB. Now set UA and UB to be the ones that we would expect, which is the local algebras on A and the local algebras on B. They both commute. So UA and UB are each other's commutant. And you realize that UA or UB actually defines a von Neumann factor because, well, as the strictly largest subalgebra on the system, the only common element they share is the identity. And then one can show that the definition of the two algebras generating the Hilbert space, generating all the operators on the Hilbert space is basically this. UA union UB is the span of all possible products of the two algebras. And if you take the bicommutant, you will get the entire Hilbert space on HA tensor HB. Actually, this example comes back to something that I mentioned earlier. So remember that this, wait, let me see, can I write? Yes, this and this are local algebras, right? So they don't include, for example, non-local entangling operations that act on both sides. Which means that if you don't take the bicommutant, you actually don't get everything here because here actually includes everything that has the operators that can entangle, so-called in quantum information language, it can entangle. While here, kind of you only contains stuff that looks like this. So really the bicommutant thing is a very important object because otherwise, in a way, you don't really get all the possible bounded operators acting on the total Hilbert space. Okay, I am 20 minutes in. I think I'm good. And now I'm actually going to say something stronger. Okay, so now suppose you don't even start with a tensor product Hilbert spaces. You only have the so-called the big Hilbert space coming from the GNS. But you still have commuting algebras and in such a way that the bicommutant is a subalgebras of the bounded operators acting on some Hilbert space. Okay. And then now since each local algebra on A and B are von Neumann algebras, they are also associated to some bounded operators acting on Hilbert spaces, say HA and HB, which has nothing to do a priori with H. And it turns out that in some cases, it is possible to do a tensor product decomposition whenever this thing arises. So this is actually saying that sometimes, even if you don't know how to do the bipartition, if you know how the algebra looks like, you can actually do the bipartition coming from the operator algebraic perspective. So equation 18 actually tells you that there is a natural way. If you know UA and UB are certain bounded operators on some other smaller Hilbert spaces, then you can actually do the bipartition of the big Hilbert space and think of the joint algebra of observables as actually a tensor product of each. Of course, if you talk about quantum field theory, there's some subtleties here and there, but the point is that The reason why this result is slightly stronger is that you don't even sometimes you don't even need to assume that you can do you already have a bipartition to start with. And this is really back to what we were talking about in the first session, in that the notion of bipartition or the notion of a subsystem can be really defined in terms of what operations are allowed in your hands. Okay. Now I'm going to go to a very nice thought experiment based on the lecture notes by Jonathan Sorse. And this is actually really the way I started learning about von Neumann algebras, which is that now suppose think about Hilbert space on Earth. So imagine we have a single Hilbert space. Give me a second. Yeah.
All right, we're back.
Yeah, thank you. So let me, now that all the basic definitions are out, let me show you a thought experiment that I recently learned. And this, I think, a very nice way of thinking about why we want to think about von Neumann algebras at all. Like, even if you do this from a fundamental perspective. Now, so a version 1 of the thought experiment is that suppose I have a Hilbert space on Earth, okay? Now, if we ask ourselves, what are the operators accessible to us, and do we have density operators? I hope everyone is convinced that, well, there's no problem, right? At the very least, we have the von Neumann algebras that is made of the bounded operators acting on this Hilbert space, okay? And the density operators actually is inside this algebra, right? Because density operators are Hermitian and also unit trace. So they are actually elements of the bounded operators acting on the same Hilbert space. So first, it is nice that you can think of density operators as themselves elements of the algebra of observables. So you really don't, you really can think of just bounded operators acting on Hilbert space as giving you everything. But now I'm gonna ask the next question. Now suppose you have a tensor copy of another Hilbert space, but it's now on Neptune, okay? And I put a symbol Neptune there, that's not psi. So if I ask yourself, what are the operators accessible to us, right? Well, you will still say the same thing, right? Since I'm on Earth, I can only do operations on Earth, which means that my local algebras should be just the bounded operators on Earth tensor the identity on Neptune, because I cannot do anything on Neptune, okay? But now if I ask, do I have density operators? I'm not sure if I should give a 5-second pause just to think about this a little bit, but I hope the face I put there should convince you that it is actually not trivial.
But you can, like in U-Earth, you can have operators that look like density operators for the Earth Hilbert space and act like an identity outside, but it's not normalized anymore. Yeah.
Exactly. So the problem is it really depends on whether that side is finite dimensional or infinite dimensional, right? If it is finite dimensional, then no problem. Why? Because I'll just take a density operator, the density operator on a joint system to be whatever there is a density operator on the Earth's copy. I just divided by D. This is still a bounded operator on Earth, and then I just put the D on the other side. So this actually defines a density operator on Earth tensor maximally mixed state on the other side, right? So it's just a product state of two density matrices. But the problem is if you have infinite dimensional vector space there, Hilbert space there, then identity is not trace class, so you can't do this trick anymore. Which means that unless you somehow are able to go to Neptune and do whatever nonsense, you really don't have access to even a good notion of density matrices over there unless you really know something about what the quantum system on far away. Marek already mentioned, basically this is the statement that in general, rho is not normalizable if you want to think of density matrices as basically an element elements of the bounded operators that you have access with. And this thought experiment is actually very important, because if you think about it, right, we still can define expectation value in the following way, right? So if I have an operator that is a tensor identity on Neptune, then you can still define expectation value with respect to rho tensor identity, even though this is not quite a state, to be consistent with just the local trace on Earth, right? You can actually define, you can just pretend it is finite dimensional, take the trace, and you can actually consistently make this definition. And in fact, you can vary rho and you can vary A to span the whole bounded operators, and this still works. So really, what this is telling you is that you can still consistently assign what we call an effective expectation values on such an operator, even though we don't have access to the other side. And this assignment, I would call it, according to the high energy physicists, the renormalization procedure. You basically renormalize the density operator in such a way that you would regard rho as effectively a density matrix. So it is a renormalized density operator if it consistently gives the correct expectation value that you expect only on the Earth. Okay. Now, if you do the same thing, but now in the most general level, I give you a von Neumann algebra A that is associated to a restricted observables. So for example, in the previous one, it would have been the Hilbert's, just a tensor product of bounded operators on Earth times the identity. But more generally, this could have been just a local algebras of a quantum field theory. Okay, now, question one, you don't have to answer anymore because I'm giving you these restricted algebras. But now, now you ask yourself, do we have density operators, or at least the renormalized one? And it turns out that this thought experiment, the answer to them is exactly the Murray von Neumann classification of the von Neumann factors from the 1936. This is the one that gives you different types of von Neumann algebras. And the idea is that if you have a von Neumann factor, so the classification is based on the factors. So you say that it is a type 1 factor if your renormalization procedure always turns some positive operator rho into either pure states or mixed states, renormalized or otherwise, right? It is type 2 if you don't have a renormalized pure states, but at the very least, you might still have renormalized mixed states. And it is type 3, which is the case for quantum field theory, if there exists no renormalizable states at all. So this is actually the same statement as in quantum field theory. There is actually no way to take the trace of a local observables. Or you might have heard people saying that there's no density operators at all in quantum field theory associated to the local observables. And we say that it is a finite von Neumann factor if every positive operator is a renormalizable state. If it is infinite, if at least one of them is not normalizable. So you realize that in particular, it is infinite the moment the identity operator is not normalizable, right? And I hope if you want to know more about this, please look at the lecture notes I put on the citation. But this is actually a very different way of how people normally explain type 1, type 2, and type 3 von Neumann algebras, which is, if you have ever heard about it, it is in terms of the existence of some projectors on the algebras. And the way you make this connection is actually exactly the culprit is because of the trace. The thing is, if you want to take an expectation value, in finite dimensions, you need to take a trace. And if you want to take expectation value, you need to take the trace of an operator times the density matrices. But if you don't have the density matrices, then first of all, you might want to try to come up with what we call the renormalized trace, which works with renormalized density matrices. And if this still doesn't work, then you're gone. So for example, to make connections with the more mathematical treatment of von Neumann algebras, basically what you are asking is the existence of what we call the renormalized trace, which is basically something acting on positive operators that can spit out positive real numbers from 0 to infinity, and this behaves like a trace. So you realize that this tau actually looks like a algebraic state, except that it only acts on the positive operators, and it only spits out not generic complex numbers, but only positive real numbers, not negative real numbers.
So Erickson, is the characteristic of the tau is that it doesn't map the identity to, it maps the identities to infinity, right? In other words, it's undefined.
That's right. So for example, in type, so that's why you need to include the identity as the output of your trace. So if you take in identity, it's going to spit out infinity. That's right. So for example, in finite dimensional quantum system, we have what we call type 1n. So this renormalized trace will take every finite rank, every projector and will spit out an integer, which is what we expect, right? You take any finite rank projectors, this thing is just going to evaluate how many non-zero diagonals are there, right? It is type 1 infinity if at least one of the projectors is infinity. And as Peter mentioned, for example, if you take a harmonic oscillator, right? It has an identity operator and it is an infinite rank projector because it has infinitely many diagonals and it will spit out n equals to infinity. Now, if it is type 2, there's two main factors, which is type 2.1 and type 2 infinity. Type 2.1 is when any projector you put in is going to spit out anything between 0 and 1. And this is actually highly non-trivial, and I'm not sure if I will be able to go through this next week, but this construction is very explicit. It has to do with the fact that type 2 von Neumann algebras is associated to, has no irreducible representations. And it is type 2 infinity if something similar happens. So it can spit out anything between 0 to infinity. Now, in type 3, if you put any projector in, it will either spit out 0 or it will spit out infinity. The technical way of thinking about this is that basically in type 3 von Neumann algebras, you cannot find a finite rank projectors. All projectors must be either trivial, which is the 0 operator, or infinite rank projectors. So this is basically a characteristic of quantum field theory.
Yeah.
Okay, so this is really two ways of making the connection between the existence of renormalized trace versus renormalized density operators. Is there a question?
Yeah.
Yep.
So at some point we started talking about projectors. Like what's the motivation to specifically think about projectors?
Yeah, so this one is not clear from what I'm presenting today, but the classification of von Neumann algebra, von Neumann factors in terms of type 1 to type 3 was originally done by classifying what kind of projection operators you have in your algebras. So in finite dimension, we have finite rank projectors, and then in type 2 and type 3, you have more complicated projectors. And this has to do with the fact that you can build local algebras of this kind by many tensor products of qubits. And studying how these things projects to subsystems is how the von Neumann algebras was originally classified. But what I was trying to advertise earlier was to understand this in terms of the existence of density operators. So unfortunately, I probably couldn't justify as well why I should be talking about projectors here beyond the fact that this is the original Murray von Neumann classification of the type of the different types of factors.
Okay, thank you.
Yep. Now, as I mentioned earlier, where can you find these kind of different types of von Neumann algebras? So type 1n, the finite dimensional quantum systems. Type 1 infinity is the quantum harmonic oscillators because it has all the good properties of finite dimensions, except maybe, for example, it has infinite projectors like the identity. And then in type 2 and type 3 is necessarily infinite dimensional. So if you study, for example, infinite spin chains, right, it's going to fall under type 2 algebras. So this is something that people in the many body physics have understood for many years. And in type 3 is basically what we are familiar with in quantum field theory. So I would I put some references here on some of the stuff that you might want to look into. And there's also recent progress in quantum gravity here, where you can use what they call the cross product construction to convert type 3 into type two von Neumann algebras, which amounts to including an external observer on your quantum system. So this is something that is a very hot topic in quantum gravity community. But the technique itself has nothing to do with quantum gravity. It's purely mathematical. It is part of the Tomita-Takesaki modular theory. And now that I'm almost done, so I'm just gonna close this. Okay, first of all, I would say that at this point, it is sort of like a cliffhanger. And I think there's no real way to really finish the topic of the von Neumann algebra introductory level without going through what we call the Tomita-Takesaki modular theory, which I'm going to do in 2 weeks. But before I leave the cliffhanger, I'm gonna talk a little bit about quantum channels with operator algebras. So converting to operator algebraic language is really only as useful as being able to work with them the way we think about Heisenberg picture, right? So we want to, for example, think about quantum channels in terms of the Heisenberg representation. So if you have a quantum channel, this is traditionally a completely positive trace preserving map from density matrices to density matrices. So you might be familiar with what we call the Krauss representation of the channel. And then when you take expectation values with respect to the some operator O, you realize that just by properties of the Hilbert-Smith inner product, when you take the trace, you can actually define what we call the adjoint channel, which acts on the operators themselves. So if you think of the quantum channel as evolving the state, now the adjoint channel evolves the operator and keep the state static. So this is one way to generalize the Heisenberg picture into the language of quantum channels. But if you want to be more precise in the von Neumann algebraic language, a quantum channel is really a normal, unital, completely positive map between two von Neumann algebras. So the completely positive one is sort of necessary coming from the CPTP property of the original channel. The unital part is also necessary, but the normality is a technical term that you need to make sure that things converge properly. So for quantum mechanical purposes, this has to do with the fact that the adjoint channel. So let me say this more carefully. So in the language of operator algebras, a quantum channel is a map between algebras. So the adjoint is actually a map between states. So you can see that in the remark, I put here that the quantum channel on the von Neumann algebra is actually would have corresponded to the adjoint channel in the usual language and the vice versa. But the crucial thing is that the adjoint channel of the algebraic quantum channel is something that maps normal states to normal states. So normal states are those that have good convergence property at the level of matrix elements, and you really need this to do quantum mechanics properly. Now, in finite dimensions, you never need to bother with this, but in quantum field theory, for example, or in thermodynamic limit of spin chains, if you don't have normal states, you're in trouble. Basically, you can't even do quantum mechanics properly. And one of the most well-known or the archetypical quantum channel in the operator algebraic language is called the conditional expectation. It's actually sounding very mysterious compared to what we are used to, but a conditional expectation is really a positive linear map with the property that the action on products of 3 elements actually amounts to the action only on the central one if A and C is in the output algebra and B is in the input algebras. And it takes, it has a fixed point if A is already inside the output. So roughly speaking, what this does is that a conditional expectation from the algebra 1 to algebra 2, typically the algebra 1 being bigger, what it does is that it always kills off all the components of algebra 1 that is outside algebra of A2. And I will give you one example before I close this presentation, is that to make this definition easier to digest, let us first define what we call a tracial state. It is a very useful state in algebraic framework is that a threshold state is basically a quantum state, an algebraic state, with actually the property that you expect from a trace, which is that tau acting on AB is the same as tau of BA. So if you set the algebra to be, for example, the bounded operators, and the Hilbert space is finite dimensional, then you realize that the threshold state acting on, say, the maximally mixed state is going to be basically give you something that is proportional to the original trace that we are used to. So whenever trace exists, the threshold state is just proportional to the trace. And why do I want to go through the pain of this? Because remember, a partial trace is a quantum channel. And you can find the corresponding adjoint channel. And therefore, you must be able to do this in the language of operator algebras. So the way we are going to do this is to do it something like this. So you start with a double copy, and you set the algebra of U1 to be the bounded operators on the total Hilbert space, and U2 will just be on the subsystem. Okay? Okay, maybe I should have changed A and B to be H1 and H2. So maybe this should be 1 and 2, maybe. And then now you are going to define a partial trace over B. So here is, at this point, this trace of B is just a notation where you take two elements of an algebra. There is a tensor product in the joint algebra, and you're just going to define it to be A, tensor the action of a threshold state on B. So this might look like overkill, but now this is the catch. Remember that a subalgebra, the bounded operator on one subsystem Hilbert space can be viewed as a tensor identity on the whole system. Then you can view now this map trace of B to be a conditional expectation, because now you just evaluate them directly. Actually, B should be 2. You take this map, you apply it by identifying it with the larger algebra, because remember, we are in U1. We are in the bigger algebra here. So let me put it here. And then just by linearity in finite dimensions, you can do this easily. And then you realize that just by properties of tensor product and linearity, you can actually write this as the action of a threshold state. And then since it is a linear object, you can put this thing in. And then you realize that this exactly follows what you will expect from a conditional expectation. And of course, there's another property that you need to verify, which is that the expectation value acting on just the subsystem is already itself. And so here you see that the partial trace in the von Neumann algebra language is basically a conditional is nothing but a conditional expectation with defined by equation 25. So I hope this example convinces you that the operator algebra language can equally make a lot of the familiar objects possible. And more importantly, it might look actually quite different from what we are used to. And I think I'm going to leave this here because it's already 10:50. But I'm just going to say that I didn't cover many things that are very important. So for example, if you look at this set of lecture notes by Nas Kens, you realize that he talks about star factor theory, Jones index, or even connections to capacities of quantum channel in the von Neumann algebra language. And you can also use von Neumann algebras to understand thermodynamic limits, for example, in many body systems, topological order. And more importantly, you can also do a lot of stuff in quantum field theory and also generic data processing inequalities for von Neumann algebras. These links are live, so when I send out the PDF, you can take a look at themselves. And some of the references I use, I also put it here, and I think I'll leave it here. Thanks.
All right. If there's any questions, we can have some questions now. Thank you very much, Erickson. I will close the recording here. Thank you.